Hi, greetings everyone. So we were discussing photolithography in the last session, and then we have also seen the e-beam lithography, just a function of that, a schematic how the electrons are used to pattern or used for patterning different materials on the substrate, and a little bit about SU8, right, and the difference between negative photoresist and SU8 to an extent. I promised you that we will look into the soft lithography, and we will also look into the mask alignment, right. So, let us first understand the soft lithography part, and then we will go to the mask aligner part. What does mean, what does that mean is that if there are multiple masks, how you will align the wafer with respect to the mask, and if you have first mask and you have patterned a certain material on a substrate, if you want to deposit another material and exactly on the top of the device, the material should be focused, right. The pattern for the second material should be in alignment with the pattern of the first material. How can we align the entire wafer with respect to mask? So, we will look into that. Let us not worry about it right now. Right now we need to understand what is soft lithography, right. So, if you see the screen, until now we have seen the contact based lithography. If you see the screen, please, contact lithography, right, lithography, in which I told you about the masks, right, and mask are bright field mask and dark field mask. This much we know, correct. Now, what is a soft lithography? Let us look into soft lithography. So, you have, as usual, we take silicon as our substrate, and then we grow silicon dioxide, okay. Then the next part is we will perform a photolithography, normal lithography, let us see. So, we have to coat the or spin coat the photoresist, right. Let us spin coat photoresist. So, we will spin coat the photoresist, as you can see on this image, and let us say photoresist looks like this. Okay. Now, we create a step. So, for creating step, what is what we need to do? We take a mask, and we say that the mask looks like this. Okay, this is your mask. Mask, and then you expose the photoresist with ultraviolet light. You expose the photoresist with ultraviolet light, and assuming it is a positive photoresist, then you develop it, right. You unload the mask and develop the photoresist in a photoresist developer. What you will get? You will get is that correct? The unexposed region, right, became stronger, and the exposed region, which is region that UV light will pass through, will get weaker and will get developed, correct. So, this is now what we have. So, when we start by spin coating photoresist, you need to always understand that follows a soft bake at 95 degree centigrade 1 minute on hot plate, and then you load the mask followed by UV exposure, then unload the mask, develop the photoresist by dipping the wafer in photoresist developer. This is a positive photoresist. So, we have positive photoresist developer followed by hard bake. Hard bake is done at 120 degree centigrade 1 minute on hot plate, correct. Now, our idea is to create a step and to do that, let us say the next step in this form. The next step is we will dip this wafer in silicon dioxide etchant. What is silicon dioxide etchant? Do you remember? BHF, right, buffer hydrofluoric acid. So, when you do that, what you will get? You will have your photoresist intact, right, because photoresist should have a high etch resistance. Photoresist should have a high etch resistance. So, it is resistant against the chemical which is buffer hydrofluoric acid. It should not etch, and the SiO2 below buffer hydrofluoric acid is protected, but the SiO2 that was not covered by photoresist is gone. Same thing happens here also, you see in the back side, right, the SiO2 from the back side is also etched when we dip the wafer in BHF, right. Now, the next step is that you strip the photoresist by dipping the wafer in acetone. You strip the photoresist by dipping the wafer in acetone. So, if you dip the wafer, this wafer, let us say we give the name A, B, C, D, E, F. So, the E, when we dip in acetone, the photoresist will get stripped off, and what we will have is the silicon dioxide. Photoresist that gets stripped off, and what we have is the silicon dioxide as a step on the silicon, all right. Now, this is our mold, okay. What we will call this as a mold, okay. Now, if I want to have a device, let us say a soft material that should look like this, okay. A soft material that has pattern like this. This is what I want, okay. This is what I want. So, what should I do? If I have a mold that we have seen previously, in which the silicon dioxide step was created, right. You see this one, the mold silicon dioxide step was created, which is F, this one. Then if I take this wafer and pour PDMS, okay, PDMS is also called a silicon, SiLicone, this is SiO2 silicon, and then we pour PDMS over the substrate and then spin coat it. Okay. We pour PDMS over the substrate and spin coat it. After spin coating, we cure it. In PDMS data sheet, you will find the parameters for curing the PDMS. Okay. So, once you cure it by heating it at certain temperature in an oven, right, then you can strip this off. You can strip PDMS from the mold. If you do that, you see, you have to strip it off. Then what you will have? You will have PDMS like what we want in this final pattern, right. Of course, do not worry about the thickness and all these things. So, now point is that this is one time you have created this pattern. So, when I strip this off, strip it off from the substrate, what I will have? I will have my mold back, correct. See that when I strip this PDMS off, I will have my mold back. So, if I have my mold back, can I pour PDMS again? I can again pour PDMS, is not it? So, I am again pouring PDMS. And I am curing it after pouring. After curing, I am stripping it off. So, if I strip it off, I will have my pattern once again. The one that I want, I am repeating it again and again and again, right. How? By stripping this PDMS off. If I strip PDMS from this mold after curing it, what I will have? I will have my mold back. That means every time we are patterning PDMS, right, but we are not using the UV light, we are not using the photoresist, we are not doing soft bake, we are not doing hard bake, we are not using mask, alignment, nothing. Just from the mold you keep on creating the PDMS structures. This is called the soft lithography. Got it? This is called the soft lithography. So, easy, you understood. If once you create a mold, you can use this mold for n number of times till the mold does not break. If mold breaks, then we have to start again. So, this is about the soft lithography. Now, let us see a very important point, which is your patterning. How you will pattern different materials and how you will align it, right, that is something that we need to see. So, let us understand. Okay. So, we will fabricate, we will go to the one more slide back. Okay. So, we will fabricate we can take an example of a chip with micro heater, right, then an insulating material insulating material okay. The micro heater is of let us say nickel. Then on top of that we want to have interdigital electrodes. Okay. This is the contact of the interdigital electrodes. These are cross section schematic. So, let us not worry too much. Okay. This can be the contact for the IDEs, interdigital electrodes. Okay. So, if I have a top view, it will look something like this. Okay. And then on top of this, there is insulating material everywhere. Okay. Then you open the contact area, this one and this one, and on that top of this you deposit a metal and you create interdigitated electrodes. Like this, all right. It is complicated, no? So, if I draw it here without insulating material, it looks like this. Okay. Okay, like this. But understand that the below the interdigitated electrodes, these are contact pads for interdigitated electrodes, these are contact pad for the heater. So, we said heater contact pad 1. So, let us say HC1, heater contact pad 2 HC2, IDE contact pad 1, IDE contact pad 2, right. So, between interdigital electrodes and a heater, since both are metals, if I deposit directly metal over metal, I will have a short circuit, right. So, there should be an insulating material below it, and this is what we want to create. We want to also make sure that when we deposit the insulating material after micro heater, the contact pads, right, the contact pads should be opened, because otherwise you cannot take the contact from your heater contact 1 and heater contact 2 if it is covered by the insulator. So, once you have silicon dioxide as an insulating material, you have to perform photolithography and open the heater contact 1 and open the heater contact 2. Now, important stuff here is that this should be properly aligned. That means that the interdigitated electrode should be in on the top of the micro heater. If there is a misalignment, it is not okay, right. If there is a misalignment, it is not okay. So, how to align this thing? That is a question, is not it? So, for that, if you see, until now whatever mask we were drawing, we always had alignment mark onto the mask. So, let us say this is the first alignment mark, this is the second alignment mark, this is the third alignment mark. Okay. Now, we think that there is a triangle, then there is a smaller triangle and even a smaller triangle, then the second triangle. Alright. So, finally, our wafer on which we are patterning this triangles, right, it should look like this. 3 triangles, first one, second one, third, all in the center of the first triangle, right. Just to make our life easier, right, I am just drawing a little bit bigger triangle. So, we understand first one, second one, third one. So, we have big triangle, smaller triangle and smaller triangle like this. You see that this mask, so mask 3, mask 2 and mask 1, all 3 mask is having what? Alignment mark. This plus is a alignment mark. Okay. Instead of plus, you can have circle also, you can have square also, whatever you feel is good for aligning your wafer, you can use that one. So, now you have plus, you can have many alignment mark at different places. Okay. So, the first time, for the first time when you take the wafer, spin coat with photoresist and then align with the mask 1, align with mask 1, what you will do? We have a wafer, okay, wafer, oxidized silicon wafer, let us say, and I do not like too bad drawings as well. Okay. So, this is your silicon dioxide and you have, let us say, one metal here, this is your metal 1, silicon, silicon dioxide, silicon dioxide. This is the wafer that we have. Okay. And what do we want? All 3 triangles should align such that the smaller triangle where mask 3 should fit in the triangle for mask 2, it should fit in the triangle for mask 1, right. These are all metal triangles. Okay. So, metal 1 is there. So, when you have first time metal, you do align. Now, you see there is a primary flat, in the TA class, right, where I taught you about the silicon wafer. After that you will be taught about the orientation of the wafer. So, please focus on that and see that how orientation of wafers are determined with respect to primary flat and secondary flat. Okay. So, now with respect to this primary flat, we will align here this one, okay, and such that the wafer not so easy to draw even a circle, isn't it? Looks like this, okay, wafer looks like this. What does it mean? That I have a wafer with metal 1 and my photoresist on metal 1, okay, on my photoresist on metal 1. So, this wafer would have photoresist below which there is a metal, you assume like that, right, it is correct. This is how it is, this one, okay. I am not drawing it here, okay, just to make you understand, I am not drawing it. So, now what you see that you have a metal, right, let us represent the metal by dots, over which you have a photoresist, So, there is a wafer with metal 1 and photoresist. You will do UV exposure, right, you will do UV exposure. What you will have when you develop the photoresist, the area which is not exposed will get stronger. So, this area which is drawn by the triangle and drawn by the alignment mark will get stronger. After that, if you dip the wafer in metal 1 etchant, what will happen? The area which is protected by photoresist will not get etched, is not it? The area which is protected by photoresist will not get etched. What does that mean? So, if I have let me draw this silicon wafer, oxide, on oxide there is a metal, and then when we use that particular mask, right, which is this mask triangle, right, then and we expose it. So, in this we can show that the photoresist is only in this direction, only left in the area which is not exposed by the UV light, correct. The photoresist will remain in the area which is not exposed by UV light, this area, and of course, alignment mark like this. Okay. There the photoresist will be there, and below the photoresist the metal will be saved. So, if I etch this by we have to do hard bake and followed by metal etching. So, metal 1, which is this one, if I dip this wafer in metal 1 etchant, what I will have? All the area, all the metal will get etched except the metal which is protected by this particular photoresist, is not it? Metal will get etched except the region which is protected by the photoresist. Correct. And then I will remove or strip of the photoresist by dipping this wafer in acetone. So, when I do that, what will I have? I will have my wafer with alignment mark and metal in the center. This is my first mask, correct. Now, the second metal here, okay, we need to again deposit a material. So, once I have this wafer with this pattern, I will deposit another metal on it. We do not worry about the short circuit here, we just want a design here, one triangle, second triangle, third triangle. Okay. So, I will deposit a metal, then photoresist spin coating, soft bake, and followed by alignment mark, right. So, alignment mask. So, I will take a wafer and align it again. Now, you do understand that I had a wafer with this alignment mark patterned on the wafer, as you can see here, correct. You can see here alignment mark is already there on the wafer. So, what happens is, if I really zoom this alignment mark, then I will see that the alignment mark is just not plus, but it looks like this. Okay. Right, like this. But here the alignment mark of mask 2 are there already, and wafer had the alignment mark from the mask 1, correct, because that area was protected. Remember, right? See this one, this alignment mark that will come on the wafer 1, because once we etch it and get the wafer, we will have a triangle and then we have the alignment mark from our wafer 1, correct, and the alignment mark of mask 2, the alignment mark of mask 2 is smaller than alignment mark of mask 1, if you have noticed, right, and the alignment mark of mask 3 will be smaller than alignment mask of mask 2. Okay. So, again the alignment mark or marks of mask 1 is greater than mask 2 is greater than mask 3, or alignment mark of mask 3 is smaller than mask 2 is smaller than mask 1, either or is correct. Why we need to have alignment mark of second mask smaller than mask 1? Because we have to make sure that the wafer that has been processed through mask 1, right, the alignment with mask 2 happens correctly, and that will happen when the alignment mark of mask 2 fits well within the alignment mark of the wafer, right. This alignment mark of the wafer and alignment mark of mask 2, right, should align well, and then only the second triangle, the image, right, this is a from the mask, right, but the wafer also has a triangle here, correct, and wafer does not only have triangle, but there is a metal on the triangle, correct. So, make sure that the alignment mark of mask 2 is smaller than alignment mark of mask 1, so that the second triangle, the design would fit exactly in the center of the triangle 1. Then you have to expose it with UV after alignment, and then you have to develop the photoresist, and when you etch it, the etchant for metal 2 should not affect the etchant for metal 1, right. Otherwise, the etchant for metal 2 should not affect the metal 1, otherwise the triangle, the bigger triangle will get etched, correct. So, now once you have that, you have a wafer with 2 triangles and 2 alignment marks like this aligned in the middle of the first alignment mark, 2 triangles, 2 alignment mark. Now, you again deposit another metal, right, deposit another metal, spin coat photoresist, soft bake it, align it with the third mask, right, and you already know that my let me read out the alignment mark for the third mask, right. I told you the alignment mark of mask 3 will be smaller than mask 2, smaller than mask 1. So, my wafer would already have 2 triangles and alignment marks something on this domain and second alignment mark like this. So, the third alignment mark which is here, right, that should fit in the center of the second alignment mark, which is already there on the wafer. Then you are aligning the mask 3 with respect to the wafer that has been processed to mask 2. Once you do that, you expose it, hard bake it, develop the photoresist, hard bake, etch the metal 3. The metal 3 etchant should not affect the metal 2 or metal 1 material, right, metal 2 or metal 1 material. So, at the end of the day, when you do this, what you will have? You will have the wafer which will look like this. Of course, there are many alignment marks. I just for ease of representation, I have just drawn 2 plus, okay, but this is how the process is done. Now, it is everything is on a very large scale. Actually, the dimensions are way smaller than what you can see on this particular screen, right, particularly the alignment mark is concerned. So, this is how the alignment is done, and that is why the mask, the wafer has to be aligned with respect to the mask. Okay. Mask is stationary and we can move the wafer. Once you align the wafer, then you make a hard contact. Until that, you have some spacing between your mask and your wafer, so that you can rotate the wafer, you can move in x axis, you can move in y axis. Okay. And once it is done, then there is a hard contact between, when the alignment is done, there is a hard contact between wafer and your mask. Okay. There is a hard contact between the wafer and your mask once the alignment is done. Okay. So, now I hope that you got some idea about how the alignment mark works, what is the role of the alignment mark when we talk about the photolithography. Okay. So, now we will stop here, and in the next class I will tell you how the SU8 can be used as a mold. We have seen silicon as a mold, right. What about SU8 as a mold? Once we understand SU8 as a mold, we will quickly cover the micro machining session, and in that we will be looking at the bulk micro machining, surface micro machining, and then moving forward we will understand the chemical vapor depositions. Now, once you grab all this thing, understand it, digest it, then we will go into the neural part, where you understand what are the signals, how the signals can be captured or acquired with the device, and how it can be processed further. So, till then you take care. I will see you in the next class. If you have any questions, ask me through the NPTEL portal, and I hope that you understood the importance of the alignment marks, you understood what is soft lithography, and you are not getting too much bored. It is little bit different than the traditional way of understanding the different topics in different courses, right, because it has a mixture of the chemistry, because lot of chemicals are used, right, right recipes, right process flow, what kind of mask we need to design. So, that means you have to understand the CAD, right. We will take a class on mask designing, and then the vision, and what exactly how the device should look like, right. So, but believe me that once you understand all these things, the game will be very easy for you to play. Okay. All right. So, I will see you in the next class. Till then, cheers.